So hello everyone, and thank you for joining us today for our HashiCorp webinar, where today we'll be discussing why modern workloads need a mesh. My name is Connor Beechnell, Senior Field Marketing Manager here at HashiCorp, and I'll be your moderator for today's session. And today I'm delighted to welcome two excellent speakers. First up, we have Erkan Jaffer, who's one of our Senior Solution Engineers. And today he's joined by Christoph Poole, who's our Staff Solution Engineer and Console Specialist. And they'll be your presenters today. In terms of the agenda, Erkan will kick things off with a general overview of HashiCorp before handing over to Christoph, who'll then get into some console-specific content before giving us a live demo. And after around 45 minutes, we'll wrap up for a live Q&A session at the end. If you do have any questions throughout the presentation, please post them in the Q&A box provided, and we'll answer those at the end, as I say. Lastly, please note this webinar is being recorded and we'll send it out to everyone via email after it's been processed, usually within 24 hours. So with that, over to you, Erkan.
Thank you so much for that intro, Connor. Erkan Jaffer, I'm a Senior Solutions Engineer based out of Stockholm, Sweden. I cover the European emerging markets together with a number of colleagues. And I will be doing an introduction today, which is going to be continued by my colleague, Christoph Poole, who's going to be talking about why modern workloads need a mesh. But prior to that, we're going to talk a little bit about some of the transition or why HashiCorp actually exists. And if you look at how organizations transition today, it's essentially becoming more and more complex in terms of the amount of clouds and how to consistently manage those. And so looking at what HashiCorp does today, you have a broad set of tools that are available across this transition that allows for you to manage infrastructure as a code for provisioning on any cloud, which is one of the products that HashiCorp provides, which is called Terraform. And from a security point of perspective, another very important technology is our secrets management capability, which allows for managing secrets in any infrastructure using a product called Vault. And also what we're going to be focusing on today is going to be a lot around service networking. And Christoph is going to do a deep dive or a bit more digging into service networking and talk a little bit about why modern workloads need a mesh. So this is going to be a very interesting session and talking about the capabilities of one of our products in the networking area. And also we have, from a product's point of perspective, another product called Nomad, which is a workload orchestrator, which allows for you to orchestrate any application in any infrastructure environment. A very flexible tool that has a lot of flexibility and simpleness to it. That is also a reason why it's a very popular tool. And in addition, we actually have just recently released two new products, one of which is called Boundary. Boundary's main purpose is to allow for secure remote access from users to devices or systems in a secure fashion. So historically, this has been pretty complex. With Boundary, we will now eliminate the need for trying to place classical equipment and security mechanisms by trying to create a perimeter surrounding the important systems and the devices. Instead, we will use a technology that allows for a gateway using an authentication mechanism for users to easily put them into the right place. And as the cloud transition goes from a high trust environment to a low trust environment, this sort of remote access capabilities becomes more and more important. So this was announced at HashiConf in the middle of October. So I would urge you to read more about that as well. Another new product is our Waypoint offering. So essentially it's a workflow manager to help you build, deploy, and manage releases within your continuous integration and development pipeline. So what's very interesting about it is that it's going to bridge a gap which has previously not existed in the market. So another very interesting tool from HashiCorp that is out there for you to be able to use. Then we have our Packer tool, which allows for you to build automated machine images in environments which can be reused in public clouds or in your own bare metal environments as well. And then we obviously have the development environments capabilities, which is Vagrant, which allows for you to specify any type of development environments which can be used for creating your applications and making sure that they have the right running criteria. So looking at this product portfolio, all of these products are available in open source and for free for our customers. This means that you can at any time just go to HashiCorp.com and just have the binaries downloaded to any one of these. But not only that, in addition to being open source and free, these products also have a great community surrounding a lot of people that continuously brings information online. So a lot of things that you're doing will always be easy to search for because of the fact that the products are not only open source and free, but they have great adoption across the world. So if you look at what HashiCorp does today, the vast majority of our focus lies in developing our open source capabilities, which is what the majority of users across the globe know us mainly about. But what is also very interesting, in addition to this, is that every single one of these products, except for Packer and Vagrant, is or will be offering enterprise capabilities. Now, today, from an enterprise capability perspective, those products that offer additional features that we have put a lot of development efforts in are the ones bracketed inside of orange. So Terraform, Vault, Consul, and Nomad are products that are offered in enterprise versions. And these products are, because they are so critical in infrastructure provisioning, secrets management, software-defined application networking, and also workload orchestration, they sometimes require additional capabilities that are beyond the open source and free versions. And this could be related to compliance, collaboration capabilities, which would be required for anybody to do more things than the free versions. So great products and very, very liked, and that is something to take a look at. Also, before I move on to the next slide, I would just like to say that if you want to learn any of these products, we have a portal called learn.hashicorp.com, which allows for you to, for free, get in there and learning the basics of these products and how to navigate around them, how to install them in your environment, and making sure that you learn the benefits of each and every single one of these. So learn.hashicorp.com is one of our very popular web pages, which allows for you to do training online, absolutely for free. Talking a little bit about HashiCorp, we was founded 2012. Today we are over 1,000 employees. I'm not sure about the exact number, but it should be just over 1,000. We have to date around $350 million of funding, and we are not a publicly traded company. So currently we are a privately traded company. And what we aim to do is essentially releasing technologies that allows for businesses to enable their transformation strategies using something called the cloud operating model. And this is something that we are going to be discussing before I hand it over to Christoph. And looking at the infrastructure in general, the way it was back in the days, or the old way of thinking regarding this, was that it used to be easy because you had a number of resources that you had to manage, and IT operations was somehow a little bit of the gatekeeper. Now, if you look at my background here, you will see that I have the great wall that protects the 7 kingdoms from the attackers from the north, the White Walkers and what have you not. Now, that is a typical gatekeeping function, but without giving away too many spoilers, a gatekeeping function only is there and can only be efficient to a certain degree, because looking at how the infrastructures evolve today, it's not really that much of static environments. And non-static environments will mean that static gatekeeping will not no longer be adequate. You need something that is dynamic, and dynamic means automation in this case. So when we talk about the cloud operating model, we're talking about enabling customers to automatically provision infrastructure in dynamic environments and making sure that using our technology, they can reach a sort of infrastructure automation, which is relevant for right type of growth and being able to migrate from older workloads to newer workloads and new infrastructures. Taking a look at some of the products that we have enterprise capabilities across today, I would split them up into four different type of challenges. So looking at the very bottom here, from a operations point of perspective, a lot of legacy environment has been with dedicated servers, very homogeneous environment. And looking at how a dynamic environment would look, it would mainly be capacity on demand, that you have your departments or different development departments or users have generating infrastructure upon demand whenever that's needed. Also being able to bring that down whenever that's needed. So that is a very big shift from the static to dynamic environment. And this should be in the control of the right personnel, because if everything is needing to be in a ticket-based system where operations need to manually get in there and do those changes, you're really talking about difficulties with scaling today. And the second from bottom up is the secure capabilities. Now, going from a very high trusted environment, such as perimeter-based protections and being able to put access control lists to protect certain resources and making sure that authorization is done based on IP level trust, etc., is and was a common way of protecting certain resources when you had control over those networks. Now, if you look at a public cloud, for instance, today, you will no longer have control over the network equipment that lies within the public cloud. This is a very big challenge because you essentially can't trust the network. And what you need to do now is that you need to instead form a way of granting secure access to those resources or preventing unauthorized access, but at the same time making sure that's secure. We are instead moving to an identity-based security approach instead of an IP-based security approach. And Christoph is going to be talking about the networking aspects of HashiCorp and what we provide. And looking at legacy systems, a lot of the capabilities were surrounding static IPs and how to allow for IP addresses to have connectivity over specific ports to other IP addresses. Now, that was probably manageable with small applications or smaller environments, and also where you own the actual network and had the control over that. But looking at the modern enterprise today, where you have your applications, where you have your different type of cloud environments, a service-based approach where you're not dependent upon the actual IP address of the service or the servers or the instances or the clusters that you have in place, instead looking at the actual services. And those services could be domain names, or it could be clients that are running consoles, and making sure that connectivity is created across based on service approval and allowing of different type of rule sets based on non-IP, but rather the service name or the service type, which is something that Christoph is going to be talking a lot about. And last but not least, the green one, which is the development aspect, how you can move it from a dedicated infrastructure where you have the capabilities of, spinning up resources based on what you have in place. Now we're instead looking at how workloads could use resources across a different number of public clouds or bare metal environments or data centers at the same time. How you can use certain type of applications that stretch across these environments in order for you to be able to schedule workloads without having to be dependent upon a dedicated infrastructure, and make sure that resource utilization is optimal as well as efficient across your different environments. So I think I'm gonna round up just by saying that the different technologies today that are addressing these capabilities are different features depending on where you look at. Now, if you would have looked at AWS, Azure, a private cloud, or a Google Cloud environment, it all would have their own capabilities looking for how to solve these issues. Now, if you look at what we try to achieve here at HashiCorp is that we try to take those discrepancies and try to make a consistent way of working. Now, the way you would imagine is that instead of trying to use and leverage the features across the different public clouds that are uniquely created for those environments, taking a look at the technology that is very neutral and that can offer a consistent way of working regardless of what direction you choose and what direction you decide to switch to. And this is one of the biggest benefits of the HashiCorp portfolio, as well as the cloud operating model, which enables you to streamline and scale up your application delivery process. And with that being said, I'm going to round up to Christoph, which is going to be taking over and discuss about the real topic of today, which is going to be discussing a little bit about Consul and how modern workloads and why those needs a mesh. So with that being said, Christoph, are you ready to take over the stick?
I am. Just
All
give me
right.
a second. Right. Thanks for the introduction, Erkan. Welcome also from my side. I'm Christoph, based out of Germany, and today I'm going to talk with you a little bit about HashiCorp Consul, which is our service networking platform. I'm trying to describe the challenges we see in our customers when they actually try to move their applications from static monolithic applications into more dynamic applications using modern runtimes like Kubernetes, and how a service mesh can solve those challenges. So, but first of all, just let me explain why we are here where we at. So why are we talking about service mesh today? So when we look about all the various compute runtime environments we see in our customers' data centers, I would argue that like everyone who's attending this webinar right now has at least 3 of those technologies running within their on-prem data center or in their public cloud environment. Now, there's one thing that all of those compute technologies have in common, which is the network, which makes those technologies talk to each other, and which for the last decade also provided the security between all those various runtimes. Like if a bare metal machine wanted to talk to a virtual machine, it needed to pass through a classical firewall. Now, when I started with networking like 15 years ago, roughly now, this is actually like what a traditional on-premise static environment looks like. Like you have a load balancer, which provides a virtual IP, which then points at the backend to like an application tier. Potentially you have firewalls in place, and all of this is pretty much IP driven. So in this example, you have these web instances, and they all have like a virtual IP, an IP address. You know that this IP address belongs to this box, and on top of this box, this application is running. Hence, you can pretty easily identify a statically configured machine, may it be a virtual machine, may it be a bare metal server, by means of its IP address in the underlying network. And based on this IP address in classical infrastructures, authentication is done, like who is calling, authorization is done at the firewall level, like is this IP address allowed to talk to this database in this example. Now, with more modern and dynamic environments, those security controls are not necessarily like feature rich enough anymore to provide end-to-end security, right? If we're looking at like Kubernetes clusters, for instance, depending on how you configured your Kubernetes cluster, the pods don't necessarily have routable IP addresses, meaning that those pods on top of a Kubernetes cluster may all use the same source IP address, mostly like the Kubernetes node's IP address itself. So if you have different services, different applications running on top of the same Kubernetes node, like all of those potentially have the same authorization treatment at a classical IP firewall, because you can't really distinguish, is it service A or service B who's currently using this IP address to call to my database? And this pretty much leads to an over provisioning in classical IP-driven firewalls. And this is one of the challenges that a service mesh solves for you, as service meshes don't really care about IP addressing anymore, and they decouple the identity of a service from its IP address. So where did all these challenges come from? Like, many companies trying to split down their formerly monolithic applications. Why are they doing this? How was it working before? If different components of a monolithic application wanted to talk to each other, it was just a local host call, right? All the various components were running on the same box. So it was pretty easy for those to discover themselves. On the other hand, this led to long development cycles, as everything had to be coordinated between the different parts of the application. So people just started to carve down monolithic applications into microservices to get all the benefits from independent development, independent scalability of the various pieces making up this application. But with every benefit, there's also a drawback. Now those applications are not necessarily running on the same node anymore. They are running in containers, they are running parts in virtual machines, and they somehow need still talk to each other, but it's not a local host call anymore. So the first challenge that we actually see when customers are transitioning towards a microservices model towards more dynamic and agile development of applications is actually, how do my various service components find each other now that they're not on the same box anymore? The worst thing you could do to make this work in this example here is to hard code the IP address of service B into service A, which it's the worst thing. Don't do it. Especially this doesn't work anymore as soon as the application B scales independent from A. How do you perform load balancing, service discovery between those applications? So many of our customers actually are putting load balancers in between those various application tiers, which provide a virtual IP address, which you can plug into service A and let the load balancer do all the service discovery. Well, this works good, but in many cases, especially when it comes to east-west traffic within a given data center, and where you don't leverage all the added security features a load balancer may be offering, this can be potential waste of money if you're just using the load balancer for the sake of service discovery. And this is actually the first problem that we are solving with Consul. Consul itself, it has three main use cases we're tackling with Consul. Today we're going to talk about two of them. Today we're going to talk about the just introduced problem of service discovery between microservices. On top of this, we're talking about later on around the topic of service mesh, how do I secure the interconnections between my various microservices. And then we also have distributed service configuration we are offering with Consul, but we're not going to touch on this. If you're interested in this, I'm happy to follow up with you offline. Right, so how does Consul solve the problem of service discovery? How do service endpoints find each other? Consul provides a distributed service registry where service instances, as soon as they get bootstrapped, as soon as they come up, can register themselves through Consul's API, and can also instruct Consul on which IP address they are running right now, on which port they are serving which service, how they need to be treated in terms of health checking, as Consul also includes a distributed health checking model for the various services. And then if application A, in this case, wants to discover a endpoint of service B, it simply can query Consul service catalog either through the HTTP API or also for backward compatibility through Consul's DNS interface. And it just queries give me an instance of service B. And by this, as Consul has all the knowledge within its service catalog, how many of service B instances are available, where are they running, what is the health status of those, Consul can reply back to service A with a healthy endpoint of service B. Also, Consul shuffles around those results during the service discovery phase, which gives you implicitly out-of-the-box load balancing between the service tiers without having a load balancer sitting in the hot path. Obviously, this is as it is stateless load balancing. So the service discovery and the service health check and the service catalog, this is something you can like easily view at a glance with Consul's UI, where you see on one page like what services are available in my data center, and you can drill down to see where those services are running. You can see the health status of those services. And coming back to this load balancing example earlier on, like if you already have load balancers in place, or if you need the added load balancing security features like an F5 can give you, like a web application firewall, which obviously Consul, as it's not in the traffic path itself, will not offer you. Consul also offers the ability like to automate those classical networking infrastructure. For instance, with F5, we have an integration where an F5 big IP can query Consul's API and reconfigure itself during runtime, given of like how many, given on how many service endpoints of a given service are registering Consul. So with this integration into Consul service discovery, you can basically eliminate the need for this ticket-driven process. Like if an application scales, the app team calls the networking team, asks the networking team to add this endpoint in the load balancing pool. Like those ticket-driven processes can completely be eliminated by just hooking up an F5 against Consul's API, and when an application scales up or down, an F5 big IP, for instance, is smart enough to reconfigure itself completely automatic during runtime. So with this, like we have solved the problem of like how do service endpoints find each other, but still we haven't solved like more sophisticated problems, like how do we make sure that only authorized endpoints are able to talk to each other? How do we make sure that traffic, which was formerly traffic in a box and nobody needed to care about encryption as it was just localhost calls, if this traffic is now sent over the network, we somehow need to secure this as well. We need to encrypt the traffic between the various service endpoints. Potentially, we don't want to like have every team responsible for a given service endpoint to implement their own type of encryption. So we want to have this out-of-the-box encryption of traffic between service endpoints. And also making sure that only authorized traffic is allowed over the network. If you look at this little image here, you could argue that, yeah, I can authorize the traffic between those 4 services here easily by putting them in different VLANs and putting a classical IP firewall in place. Yeah, maybe that's true for only 4 services, but a normal environment consists of like thousands of services, hundreds of services, which are dynamic, which are coming and going, which appear on different runtimes. And so it's pretty challenging to keep up with those security requirements if you're still using classical IP-driven firewalls. So for Consul and the service mesh features we're adding with Consul, basically we are decoupling the service identity from its IP address. We don't actually care about IP addressing anymore. IP addressing for the service mesh is just a transport vehicle. So all the service identities are actually baked into certificates, which will be used for authentication between the service endpoints, for authorization of traffic flows between service endpoints, and also for automatic encryption of service-to-service traffic. Consul is built in a way that it really is a multi-cloud and multi-runtime service mesh. Even though I'm only demoing Consul on top of Kubernetes later on, I wanted to make clear that Consul service mesh capabilities, they are not bound to Kubernetes only. You can run a service mesh with Consul on like every runtime platform. You can set up a service mesh completely virtual machine based, even without having Kubernetes involved at all. Because one of our founders years ago, don't remember, said like for most of our customers, a service mesh is the goal of their infrastructure. Like they want to migrate everything to Kubernetes and then have the service mesh. Consul's vision is actually you can have a service mesh right now on the platform of your choice. So you don't need to first migrate to Kubernetes, to get a service mesh, you can have it right now. So how's the console service mesh actually built up? Now I'm going to dive a little bit deeper into like how it works in the bits of pieces, but not too deep. And as mentioned, whenever there's a question, feel free to use the Q&A panel. And Connor will hopefully inform me when questions appear so I can handle them right away. So in Consul, there's a clear distinction between the control plane of a service mesh and the data plane. So the control plane is pretty much what does all the heavy lifting, what does all the calculations of the system, what does the pre-calculations of service-to-service traffic, how should it look like, what is allowed, how do I handle for instance, layer 7 traffic, which is asking for a different path. So this is all pre-calculated in the console control plane, and then basically the data plane is programmed accordingly, completely in a distributed fashion. The data plane component of console is built pluggable, where we offer various integrations into various proxies. So first of all, we have a pretty tight integration into Envoy Sidecar Proxies. Envoy is pretty much the standard data plane in service meshes today, but we also offer integrations into HA Proxy, or also we offer integration like to build your application natively into a service mesh without even using a Sidecar Proxy. And there will be more to come in the future. So I mentioned earlier that we decouple the identity of a service from its IP address, and we're using certificates for service identities. Certificate management is always a pretty complicated topic, and many customers are afraid of actually managing that much of certificates. This is all completely automated in Consul. So in Consul, we are shipping an integrated CA functionality, or if you want to, you can also hook up an external CA like HashiCorp Vault or like AWS PCA. And the complete life cycle of generating service certificates and installing those in the Sidecar Proxies is handled by the Consul clients. Like the Consul clients, they will generate key material for a given service instance, they will bootstrap the proxy, they will install the certificate in the Sidecar Proxy, and they will also take care of lifecycling the certificate. So if a certificate is about to expire, the Consul client agent will be smart enough to renew the certificate for the Sidecar Proxy, completely automatic. So even though this looks like a complicated topic, it's completely like hidden within the Consul control plane. And the only thing customers need to care about is actually to decide which CA to use for the service mesh. In Consul, we have something we're calling a service access graph. And the service access graph is made up of intentions. And you can think of intentions like higher level firewall rules, where basically we can define which service endpoint is allowed to talk to which other service endpoint. Basically, it's not service endpoint, it's which service can allow to talk to which service. And this is something that automatically scales with Consul, meaning that if you have configured an intention, like service A is allowed to talk to service B, you never need to touch it again when new service endpoints appear. Because as it's not IP driven, as everything is certificate based and Consul has all the knowledge with its service discovery, once those intention is in place and you want to have it in place, applications can scale automatically and no human operator needs to like actually add some endpoints manually to these intentions. So we just recently, 2 weeks ago, released the Consul 1.9 beta, where we enriched this intention model. And whereas intentions before Consul 1.9 were on a service to service level only, like on the TCP layer between the service endpoints on a given service port. For HTTP and gRPC applications, we just recently added a feature called layer 7 intentions, where we cannot only specify which service endpoint is allowed to talk to which other service endpoint, but for HTTP driven applications, we can actually decide like which path on the other API is this service allowed to call, which methods is it allowed to use against this endpoint? Like, is it only allowed to do HTTP GET or also to HTTP PUT, for instance? And we can specify like, do there need to be some headers in place for this connection to be allowed? When it comes to integrating your applications into a service mesh, most usually we see the sidecar proxy approach. Whereas in this example here, you have next to your application running the console client agent and a sidecar proxy of your choice. As mentioned, most customers will use Envoy today. And now if a service endpoint like this web endpoint wants to talk to the database and it wants to leverage the service mesh, it would not call directly the database endpoint over the network. It would just connect to its sidecar proxy, and the sidecar proxy actually would do all the heavy lifting when it comes to service connectivity, meaning it would do the service discovery, it would take care of authenticating the traffic between the endpoints, it would take care of authorizing the traffic, like is this service call allowed? And on top of that, it would also take care of automatically encrypting the service-to-service traffic. For Kubernetes, as we will see later on, this sidecar proxy can be completely automatically injected by a mutating webhook, which we're providing. So putting this all together, like how does it work if two service endpoints want to talk to each other? First of all, like if your service bootstraps, it registers itself in console. The key material will be generated. We will generate a certificate based on the CSR, and we will bootstrap the sidecar proxy, install all the necessarily routing features, the service discovery features, everything in the sidecar proxy. And then once your service-to-service traffic starts flowing, the sidecar proxy will already know like to which service endpoint to connect. It will have a list of service endpoints available, like if you have, in this example, if you have multiple databases available, we will also like have load balancing in between those databases available. It will initiate the TLS handshake for authentication purposes, so the web service can rest assured it is talking to the database service it wants to talk to. And the database service on the other side actually knows who just initiated the connection. So with this mutual TLS handshake, the authentication piece of the service-to-service communication happened. And also we now have this encrypted channel between the sidecar proxies. The final step of service-to-service traffic authentication authorization is obviously the authorization piece. For authorization, we currently use a distributed auth-C callback model, meaning that the local sidecar proxy will call back to the console client agent to ask if like the web service is really allowed to talk to the database service. And for this, it simply extracts these Spiffy IDs, which are baked into the service certificates, presents them to the console client agent. And this one will have a cached list of intentions available for the database service. So it can reply pretty quickly if this service-to-service traffic is authorized or not. If it's authorized, traffic is being decrypted and forwarded to the final destination application. If the traffic is not authorized to flow, basically the TCP session is simply reset between the service endpoints. Starting with console 1.9, we are also pushing the authorization feature down into Envoy directly, so we don't have this auth-C callback anymore, like looking forward. So everything I just told you is true for HTTP and any TCP-driven application. So console is capable of transporting any TCP-driven application, may it be a database, may it be like a web server hosting a website. But when it comes to layer 7 traffic, we can actually add more sophisticated traffic features to the sidecar proxies. So we can add, for instance, HTTP routing, we can add traffic splitting, and we can resolve based on tags at console. So I'm not going to dive into these features right here because I'm showing all of those during the demo later on. Also, we have the capability to configure your distributed fleet of Envoy proxies in a way that you can like configure metrics and tracing and like put them to Prometheus, make them visible through Grafana, and like have all these decentralized components reporting back to your centralized component. Also in console 1.9, which is currently already in beta, so you can download it already if you want to test it out. We're adding more native visualization features to the console UI. So it's easier for human operators to just go to the console UI and see like what's the issue between my actual service endpoints, if there are a connection that is that the application tries to use, but which is denied by an intention. So this gives you a more native integration into console. For service endpoints which reside in the mesh, in the service mesh, they are like, you can think of the service mesh like an island, a virtual network island sitting on top of your environment. So not all of your applications will be in the mesh, and there are some more traditional applications or like managed databases in a public cloud environment, like mainframes, which you will not be able to include into the mesh because they are too old. So to make applications appearing in the mesh, talk to applications outside of the mesh and vice versa, Consul offers a bunch of gateways. So we have an Ingress gateway capability, which actually can expose services residing in the mesh to outside services, meaning you have this single entry point into the service mesh. For instance, if a mainframe wants to talk to something in the mesh. On the other side, we have something we're calling Terminating gateway, which actually can impersonate an external service within the service mesh. So you can use this Terminating gateway to, for instance, impersonate mainframe services within your service mesh, and the Terminating gateway would run right in front of your mainframe, and traffic towards the mainframe would be like treated completely as service mesh traffic just until the Terminating gateway. The most powerful feature and the most powerful gateway we're offering in Consul in terms of gateways, in my personal opinion, is something we're calling mesh gateway. Like if you think about how modern workloads behave and how a service mesh handles traffic between the various endpoints of a service mesh, normally there would be the need to have an any-to-any kind of connectivity between all your various environments. Now, there are circumstances where you cannot offer this any-to-any connectivity. Maybe your security team doesn't want your firewall ports to be open any-to-any between public cloud environments. Maybe you're running Kubernetes environments which have non-routable IP addresses running. So with mesh gateways, actually, we offer the capability to solve those challenges. We can offer multi-cloud Kubernetes service mesh managed centrally. We can include virtual machines and Kubernetes clusters within the same service mesh. We can even interconnect environments with overlapping IP address space, because like we only care about the service identity. We don't care about the actual IP address of an endpoint anymore in the service mesh. And you can think of the mesh gateways as being like proxy instances for all your Sidecar Proxy instances, whereas Consul Service Mesh is smart enough to decide when service to service can talk directly and when it needs to cross a mesh gateway. When it comes to the Kubernetes integration of Consul, we have a pretty tight Kubernetes integration. So first of all, we offer a Helm chart which completely automatically can bootstrap Consul on top of a Kubernetes environment. We have just before aforementioned mesh gateway functionality, which allows us to interconnect various Kubernetes clusters completely transparently and have like a single service mesh across multiple Kubernetes clusters, potentially across multiple cloud environments, and including virtual machines. And we have a feature called Consul Auto Inject, which, as we will see in the demo later on, will take care of automatically injecting the necessary Consul bits into your Kubernetes deployments. So developers don't even need to know that Consul is actually there and providing the service mesh. The webhook we are providing with Consul can simply inject the necessary Sidecar proxy and the Consul bits completely automatically. Also, pretty new in Consul 1.9, we are making our integration into Kubernetes even more native, as we now also offer CRDs where you can configure Consul in a Kubernetes native fashion through custom resource definitions. Again, this is in Consul 1.9. So the how we see Consul is basically as the single control plane for application-based networking, like building the bridge from classical environments, maybe bare metal, maybe virtual machines, all the up to really the new runtime environments like Kubernetes, like Nomad, while still providing integrations into classical networking infrastructure as load balancers, firewalls, and also more modern integrations with Sidecar Proxies, with API gateways to provide Ingress capabilities into the mesh itself. And with that, I'm diving into the demo, just having a look at the clock. Pretty short time. All right, so this is my demo environment. I have 2 Kubernetes clusters running. Each of them has Consul installed on it. I interconnected both with the Consul Mesh Gateway feature. I have them both running in GCP just for the ease of use. But those Kubernetes clusters could be like running on different cloud environments as well. It would not change the demo flow at all. On top of those, on top of my first cluster here, I have a pretty simple application running, which consists of a front end calling a backend, and this backend has like a small API endpoint. So first of all, quick intro into the Consul UI for those of you that haven't seen Consul. This is the Consul UI where you can see the services I currently have registered in my first Kubernetes cluster. So it's basically Consul itself, my mesh gateways, my front end, and my backend. I have this single pane of glass where I can switch views. I can switch to my second Kubernetes data center where I currently have nothing installed. I will do this in a second. So on my first Consul data center, as mentioned, I have this front end application and this backend application, right? This green box and this blue box. So I exposing this to the internet, so you can basically follow along if you wanted to. If I hit my front-end application on the base path, this will route me to my backend application. Now, the same is true if I'm using the /API path as my backend application. Basically, it's the demo of a monolithic application. So if I check like what's actually running on top of my Kubernetes cluster, this is the same for both Kubernetes clusters. Just want to show you how Consul looks like. I have actually running 3 Consul servers. They are running as stateful sets on top of Kubernetes. I have my mesh gateways, which I use to interconnect the both environments. I have my mutating webhook running, this guy here, and I have some Consul with a UID pods running. Those are Consul daemon sets that are running on every Kubernetes node and that are used to provide the Consul API on each Kubernetes node, basically. And obviously, I have my 2 application pods running. So what I want to do now is I want to deconstruct this monolithic application. Like I want to tear the API powered out of my application. I want to run it as a separate instance. So let me quickly deploy this API containers here. So first of all, just to show you the deployment specification, it's pretty straightforward. I'm just defining a simple Nginx container in my specification and an init container, which basically renders all the information where my pod is running, so we can see it on this, the wrong direction. All right, so quickly deploying my API, and as you can see, there's a version 1 attached to it. We will have a version 2 later on as well. So if I'm quick enough, I will see that right here, 2 init containers will start, even though I only defined 1 init container. Also, 3 application containers are about to start, even though I just configured 1 application container. So if we check how this deployment now looks like, we can see what actually is being automatically injected by Consul. If I'm going all the way up here, sorry if I'm maybe a little bit too fast, I see the init container, the one that I created manually, and then I will see another init container which was automatically injected by Consul's Kubernetes integration, which is Consul itself. So this init container actually makes sure to register this API service within Consul. As we can already see up here, it already registered the 2 instances. It will generate the service identity. It will generate the necessarily key material and the certificate, and a bootstrap configuration for Envoy itself. Now, the application containers we will see, we can see appearing is actually the one I, again, configured manually, my Nginx, and then we have a native Envoy image, which is injected by Consul automatically, and which fetches the bootstrap configuration, which the init container generated. And also we have something we're calling a lifecycle container, which is part of our Consul Kubernetes integration, which takes care of the container that it's still registered in Consul, even though when errors appear in the system. Right, so obviously the next thing I would do, I want to bring my application to life. I want my front end to now use this API part of the application as well, whenever it calls my API path. So now I have 2 options to actually get this done. I can reconfigure my front-end application, telling him, okay, if you want to talk to /API path, go to this other endpoint. But as I'm too lazy to actually reconfigure my application live, I'm going to instruct the service mesh to take care of my traffic, that whenever the front end calls the /API path, it will be rerouted not anymore to the backend application, but to this little microservice. So for this, I will install a service router in Consul, which is part of our layer 7 traffic management. And this instructs Consul to do exactly what I just mentioned. Like whenever somebody, calls the backend service, or thinks he calls the backend service, but asks for the /API path, I'm going to send the traffic to a different destination service, which in my case is the API service. Right, so yeah, how does this service router look like? It looks exactly like what it looked in the slide. So I'm not going to cheat on you during this demo, I promise. Let me quickly install this. And then what we should see happen is actually that traffic in my blue box should stay the same, whereas traffic in my red box will not be routed to my backend service anymore. It should be routed to my API service. All right, let's see what happens. Let's see what happens. We see that, okay, we see an error. This error was actually on purpose because I didn't show you something in the first place in the Consul UI. What we can see now is that we see a connection error. Connection is terminated with reset headers message. What does that mean? Actually, I configured Consul in a way that it doesn't, it's working in a whitelisting model. So I need to explicitly tell Consul which service endpoints are allowed to talk to each other. Consul normally runs in a whitelist model, meaning that traffic is denied by default. I added this deny all rule here in my intention list just to explicitly make clear that I'm only allowing traffic which is explicitly allowed. So what I need to do now, as my front end now tries to connect to my backend, even though it doesn't know it does, connect to the API endpoint, I simply need to create an intention for my front-end application to be able to talk to my backend application. And those intentions, by the way, they are replicated across all of the environment, meaning I'm configuring them in my first Kubernetes cluster right here, but they will be replicated to the second Kubernetes cluster, as we will see in a second. All right, as soon as I hit save, those intentions will be replicated across the system, and we see that I'm now rerouted to my API endpoint, even though my front end still thinks it's talking to the backend. But the layer 7 router in Consul actually takes care of rerouting the traffic. So you can think of it kind of like a distributed API gateway model we can set up within the service mesh in Consul. All right, now that we solved this, my API endpoint worked quite good for the last 30 seconds, so I'm declaring it to be version 1, and I want to improve. I want to have a version 2 of my service, which I want to deploy in a different part, in a different region, because potentially I need other cloud features. So let me quickly deploy my version 2 of the service in my second Kubernetes data center. And what you can see is that actually the same things happen again. Like my init containers are starting, the API service is being registered automatically in Consul. It still says it's unhealthy due to the Consul health checking, which is looking if the sidecar proxies are up and running and if Consul actually can send traffic to the service. So this will take some seconds before Consul will be able to send traffic to it. So if we check the tags I attached to those, I told Consul that it's like a version 2 of my service, whereas in the other data center, it's version 1. We can see that no traffic is yet sent to this new version, as Consul always tries to send traffic to the closest destination possible. And in this case, like I have API endpoints in my local data center available. So what I want to do now, I want to do traffic splitting. I mean, I want to send traffic to my new application endpoint for testing purposes. I want to look if it's working as expected. And if it's working as expected, I can like switch traffic over, or I can switch traffic back. But I don't want to have this hard cut where I switch versions with all of my customers' data in one shot. So for this to work, for my API service, actually, I'm defining a service splitter. And the service splitter instructs Consul to leverage different service subsets, like my version 1 subset and my version 2 subset, and split traffic percentage-wise between those endpoints. Yeah. How does Consul know what version 1 and version 2 subset mean? Basically, in this case here, I'm doing a filter on the meta tags I attached to the service endpoints, which instruct Consul, these are the version 1 endpoints, these are the version 2 endpoints. So let me quickly also install this service splitter. And as you can see here, I'm splitting in a 70-30% so that we actually can see something small. So as soon as I'm installing this traffic splitter, again, what we expect is to see nothing happening in my blue window, my blue box. But here in the second box, we expect that like every third call actually should toggle between the service versions. And it also should toggle between the Kubernetes clusters. Like this is my Kubernetes cluster 1. You should see that traffic for the version 1 should only be sent over to the second Kubernetes cluster. I just invoked the service splitter. It takes some seconds, and we can already see that we have a version 2 in place, and traffic gets load balanced in a 70-30% split between the two versions, while we still have the load balancing within the separate versions of a like round robin kind of fashion. All right, perfect. And as easy as it is like to split traffic between versions, it is to actually migrate applications from one Kubernetes cluster to another, or to perform a failover. So what I want to do now, I'm going to invoke my backend application right here as well on my second Kubernetes cluster, which is like the exact same thing I have running in my first Kubernetes cluster. And as soon as those become healthy, I can tear down the backend service in my first Kubernetes cluster right here, and Consul will transparently fail over to the available instances in a remote data center. So with this, yeah, it's kind of Consul's automated geo failover capabilities, which normally would resolve in like the nearest service. But if this is not available, Consul is smart enough to provide you a remote service endpoint for business continuity purposes, because like even a like bad performing application is better than a non-performing application. All right, so we can see my backend instances are up in my second data center, so I can simply tear them down in my primary data center. And what we should now see is that we transparently fail over in the upper window to my second Kubernetes data center right here. And still having the traffic split for sure between my API endpoints. And with that, I'm sorry that I ran a little over, but I hope it was interesting, and we are open for questions, Connor.
Fantastic. Thanks, Christoph. And yeah, we have a couple of great questions coming through. So I'll start very quickly at the top. Just in regard to the network infrastructure automation use case that you were showing earlier, Does this mean that you are not using the service object in Kubernetes, and instead you're just creating replicas of your pods and letting Consul communicate with them directly?
Yes, so for Consul Service Mesh, we're not using the Kubernetes service object at all. So for the service mesh part, we have the capabilities for service discovery to provide Kubernetes cross-cluster service discovery, where we can replicate service objects between various Kubernetes clusters for service discovery only. For the service mesh I just demoed, we are not relying on Kubernetes service objects at all, as like the same environment could be set up on top of virtual machines where you don't have Kubernetes service objects. Like Consul itself has a service model, which kind of compares to the Kubernetes service object, but which also allows to set up things like this on non-Kubernetes based environments. Hence we don't have the integration, or hence we don't use Kubernetes service objects at all. I hope this makes it clear.
Thanks, Christoph. The next one is, how quickly does Envoy config change with respect to the current dynamic environment when containers or service instances come and go? How does that work, and can you explain it a bit?
So how we configure Envoy is actually through Envoy's XDS API. So the Consul client agent, it offers like a gRPC interface, which has Envoy's XDS API implemented. So this is basically we are reconfiguring Envoy during runtime. So meaning that as soon as new service endpoints, which are relevant, for instance, for a downstream application, appear in Consul and they become healthy, we're going to push them down into Envoy. As soon as we, what I just did, configure a layer 7 routing object, a splitting object, this is like pushed down to the necessary envoys right away.
Perfect, thank you. Next one is just around native service mesh. Does the Ingress gateway support HTTP request tracing?
I'm not 100% sure, to be honest.
No problem. We can get back to you afterwards with a better explanation into that one. And then last but not least is, can you explain what gateway would be best to connect services between two AWS accounts? We have EKS, which orchestrates a bunch of services in one AWS account, and another AWS account which ECS services. What is the best way to connect them?
The two accounts. So pretty much, let me quickly go back. So if those are the two AWS accounts, the mesh gateway, if you don't have end-to-end routability between your ECS containers and your EKS pods, this is a pretty perfect use case for Consul's mesh gateway, where in between your accounts, you just need to open like 2 or 3 different IP addresses to communicate to each other, allocate them to the mesh gateways, and the mesh gateways can then like tunnel all the service mesh traffic in between those accounts while still allowing for end-to-end encryption. Yeah, that would be pretty much my answer to this one. So it really depends on like how those accounts are interconnected, but with mesh gateway, you can pretty much get everything working.
Great. All right. Well, thanks a lot, Christoph and Erkan as well for these great presentations and demos. With that, if you do fancy learning more about HashiCorp Consul, then I really encourage you to check out our learning platform where you can try some of these features for yourself. And you can find that at learn.hashicorp.com/console. And lastly, just a reminder, this webinar was recorded and we'll make that available on our website after processing. And I'll send you a link via email once it's ready within the next 24 hours. Okay, so I hope everyone enjoyed today's session and thanks so much for joining us. Thanks, everyone.